No, I guess I was thinking. Yeah, I mean, yeah, it's really like. We understand yes.
Okay, well, hello everyone, welcome. It's a real pleasure to be here and to welcome you to what turns out to be the inaugural physics club of this academic year. So great to see everyone, and it's particularly nice to have on this occasion Markus Aspelmeyer here from Vienna. Markus received his PhD in 2002 working in condensed matter experiment, which proved to be largely unrelated to the rest of his scientific career. He made the decision to entirely switch fields and begin a postdoc studying quantum optics and foundations of physics, foundations of quantum mechanics, so to speak, with Anton Zeilinger, the University of Vienna, where he's remained ever since. Not only did he switch fields to start new physics, he launched a brand new project in that group to start a brand new effort on what we now call cavity optomechanics, whose goal is to search for quantum mechanical effects in the motion of surprisingly large objects. And his group has had a number of major breakthroughs in that field, doing some of the first work on what you would call single phonon quantum acoustics and studying quantum effects in the center of mass motion of sort of 1 cubic micron levitated objects. That's what he'll talk about on Friday at the Yale Quantum Institute colloquium that I encourage you all to go to. Today, we're going to hear about something entirely different, as they say in Monty Python, but very exciting nevertheless. So I think the only thing left for me to say is that Markus will be here all the way through Friday. He has an official YQI on Friday schedule on Friday that you can sign up for. Tuesday, Wednesdays, and Thursday, we're trusting him to organize his own day. So we'll see how that goes. But if you want to meet with him, what that means is you can just write to him directly and set up a meeting time on those 3 days. And other than that, just welcome Markus, and we look forward to it.
Thank you so much, Jack. It's really a great pleasure being here. We had planned it just before COVID hits, and now finally we managed. And I'm really extremely glad to be here. I already had a full day of lab tours, which was very exciting, and I look forward to continuing that over the next day. So please get in touch with me for discussing more. Now, as Jack said, for something completely different, I assume typically that two types of persons in the audience, the one who find this question strange and the other ones who find the question obvious and its answer. So that's, you have to find out now to which part of the persons you belong. But before I dive into that and give some context to what I mean with that question, let's go back in time. Approximately 120 years, almost 120 years. So quantum physics was in its early glorious days. We already had a beautiful framework for explaining quantum phenomena in matter, and light was treated according to Maxwell's equations, and all was good. Until, of course, 1905, when Einstein came up with his almost. Okay. Let's see. There you go. When Einstein came up with his famous light quantum hypothesis in the 1905 paper on a heuristic viewpoint concerning the creation and transformation of light. The idea was extremely simple and beautiful, and in Einstein's own words, this is what he wrote in a letter to his dear friend Habicht, very revolutionary. The idea was to ask the question, how does entropy of the radiation field of a black body change with the volume of that box that contains the black body radiation? And he does a simple calculation and shows that the black body radiation entropy changes with volume in essentially the same way than the entropy of an ideal gas changes with volume. So by simple analogy, simply comparing those two expressions, what we know from non-interacting ideal particles with radiation, the entropy of the radiation of black body, he concludes that, you see, monochromatic radiation behaves thermodynamically as if it consisted of mutually independent energy quanta. It's this exponent here of magnitude, energy magnitude, essentially Planck's constant times the frequency. That was the argument. And if you think that's the end of the story, because that's essentially what we know, this was the famous light quantum hypothesis, and from that point on, we have the quantum theory of light. Essentially, the opposite was true. Everyone, literally everyone in the field rejected that idea. So here's a couple of quotes. Planck, 5 years essentially after the paper. The rejection of Maxwell's electromagnetic waves seems to me to be a step which, in my opinion, is not yet necessary. It's not backed by experiments. We don't need this assumption because we can explain everything by assuming the validity of quantum theory applied to matter and using Maxwell's equation for radiation phenomena, for light phenomena. 1916, 11 years after the paper, Millikan, Einstein's bold, not to say reckless light quantum hypothesis flies in the face of the thoroughly established facts of interference. So these were the days where we also had then all the beautiful X-ray interference phenomena just popping up. 1925, 20 years after the paper, Bohr. Even if Einstein sends me a cable that an irrevocable proof of the physical existence of light quanta has now been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. So it was simply not accepted at all. Now, the question at stake was, and you would say, no, well, but we had experiments after some time. No, we had the photoelectric effect. We had later the lamp shift. We had the G-2. So there were many phenomena that sort of required quantum electrodynamics to describe them. But this is definitely far from the truth, because still in the up to the 60s, there were discussions going on whether there could actually be an experiment whose outcome cannot be described by the joint assumption of quantum theory, Maxwell's theory, because at that time, it was Ed Jaynes, famous Jaynes from the Jaynes and Cummings, who actually had come up with a neoclassical theory of radiation that would describe all those existing phenomena in the context of classical physics. So there was then this famous Rochester conference in the 70s. You see this beautiful quote by Jaynes: "Physics goes forward on the shoulders of doubters, not believers. And I doubt that quantum electrodynamics is necessary." John Clauser was also at that conference, and he challenged him. He said, look, I seriously believe it is necessary. And this is also was one of the motivations for Clauser to do experiments that could actually not be explained anymore by the joint assumption of a classical theory of electromagnetic radiation and quantum theory. And this was a series of beautiful experiments back in 73, 74, on the experimental distinction between quantum and classical field theoretic predictions for the photoelectric effect, which was essentially a series of experiments where two photon correlation measurements established violation of a Cauchy-Schwarz inequality for the radiation field, which could not anymore be explained by a classical field theory. And eventually, there were beautiful follow-up experiments by L'Aspect. And if you include also the Bell tests that appeared around the same time, now in the 70s, okay, we are talking now 65 years after the publication of Einstein's light quantum hypothesis paper, it was now safe to say there is no classical alternative to a quantum description of the electromagnetic field. Message being, it takes time and it takes good experiments. The underlying question here was, just to repeat that, is it possible to have phenomena that we cannot explain by assuming the joint validity of a quantum theory and a classical theory of light? So, after this historical excursus, let's fast forward. Let's fast forward again our 120 years. Now it's the year 2023. And here are other things that we can safely assume in the current status of physics. Number one, quantum theory works. This we know. And here, one of the most beautiful examples is, of course, the validity of the quantum superposition principle on the level of individual objects. Like here, data from the lab of my colleague in Vienna, Markus Aspelmeyer, who shows quantum interference of macromolecules. So what they do is they, in the experiment, they can create quantum superpositions of the center of mass state of molecules that are literally in a superposition of being here and somewhere over there. Okay, I mean, we're talking about particles like 5 nanometers in size and being delocalized over 500 nanometers, which is an absolutely amazing demonstration of this quantum superposition principle on the level of individual particles. So every experiment so far confirms the principles of quantum theory are valid in the lab. So here's the other thing we know. general relativity works. The existing theory of gravity, as written down by Einstein as a classical field theory, is right now the best theory we have to explain and describe gravitational phenomena on all scales, be it from small gravity experiments in the lab, where essentially we just use the linear regime of Einstein's field equations, to astrophysical phenomena in extremely strong gravitational fields where the full nonlinearity of the theory is needed. These two theories are essentially right now two of the best tested theories that we have that underlie our current worldview. Now, here's another statement that is true. And now remember our story from the past. The status at the moment is concerning experiments on quantum physics and gravity. Ideally, assume experiments where you do some gravity experiments using quantum systems, for example. They all basically follow this statement here. All experiments that we have, all gravity experiments that we have, can be explained by assuming the joint validity of quantum theory and general relativity, which is a classical field theory. I give you two examples that you see what I mean. This is my favorite one. This is the so-called cow experiment after the initials of the authors Colella, Oberhauser, and Werner, that demonstrates the influence of Earth's gravitational field on the wave packet of a massive particle, a neutron in that case. The idea is very simple. Quantum mechanics 101, you have a particle, you send the particle through a classical field. What happens is that the particle wave function acquires a dynamical phase. Yeah, it's just the action that it acquires pops up in the phase. We cannot measure global phases, but we can measure phase differences. So what we do is we take the neutron, we send it through a beam splitter. A beam splitter in neutron physics is essentially a slab of a single crystal silicon. You send the neutron there, there's Bragg diffraction, there's a transmitted and a refracted beam, a diffracted beam, and you split the wave packet in two, and now you can have one branch of the wave packet traverse through one height in the gravitational field, the other one through the other height in the gravitational field. So they pick up the two branches pick up two different dynamical phases. So you generate a phase difference between the two, and this you can compare by recombining the two paths again via, again, sets of two beam splitters, recombine them and then measure. And the result is, of course, interference fringes induced by Earth's gravitational field as a function of the height difference. And the height difference you get when you just rotate this silicon crystal interferometer like that in Earth's gravitational field. Okay? There have been beautiful follow-up experiments. For example, a recent experiment by the group of Mark Kasevich, who discuss this experiment in the context of an Acharnov-Bohm experiment. I just mentioned that in passing. Now, the other type of experiments concerns gravitational redshifts. So here is a beautiful example of the Dave Wineland's group, where they asked the question, how does a clock tick depending on the height in Earth's gravitational field? And we know it ticks different when you have it at different heights in Earth's in the gravitational potential. So what they do is, what you see here is basically a atomic clock setup, optical table. You measure beautifully frequency of your atomic clock. This is what's plotted here. And then what you do is you just lift up the whole optical table. You see, you have these jacks here, and you lift it up by 30 centimeters, and you see how the frequency changes. So this is an experiment where they showed that we do have now quantum systems, we do have clocks realized through quantum systems that are sensitive to height differences in Earth's gravitational field of only 30 centimeters. And here's a beautiful example of progress, technological progress over time. If you look in the literature today, so this was in 2010, so now it's basically 13 years later. For example, in Junyi's group, they have just published the data where they see sensitivities down on the millimeter level, height level in their experiment in their lab to changes in Earth's gravitational field, which is absolutely astonishing. So this is the situation we have right now in the lab. We have quantum systems interacting with gravitational fields, doing absolutely unprecedented experiments. And yet, all of those experiments can be explained by assuming quantum theory holds and Einstein's theory of general relativity holds. There's no reason whatsoever, based on our current experimental situation, to assume that gravity would require a quantum description. Very similar, of course, to our Einstein example, it is very natural to write down a quantum theory of gravity. It's actually something that is more or less simple, yeah? But we don't have any experiment yet that would require it to be so.
Newton theory very enough.
That is right. That would be yes. It's enough. Okay? But of course we know Newton is not enough. So in the end, of course, what you want to have is want to have a full framework, and of course you can derive Newton starting from Einstein and just linearize down in non-relativistic regimes. Thanks. But this is going to be important later. So thanks for the question. Okay. So coming back to what I said in the beginning, let me just rephrase everything and just exchanging Maxwell with Einstein. This is the situation that we have. The question, can we have an experiment whose outcome cannot be described by the joint assumption of quantum theory and Einstein's theory of general relativity? Or I give you another example of another conference. It was the Rochester 72 conference I gave you before. Now we go to another famous conference, the 57 Chapel Hill conference, which was a conference that was initiated by John Wheeler and Bryce and Cecile DeWitt in 57 to discuss the status of the role of gravity in the whole context of physics, because people thought gravity had hit a dead end and no progress would be made anymore. And so they brought the people together, and there was an Austrian physicist, Goltz, who asked exactly that question. He asked, can we have phenomena which the classical theory of gravity without condensation is unable to explain? This was the question. And they actually discussed one other question at the conference also, which is, do gravitational waves exist? Do they transfer? Do they radiate energy? So these were the two big questions they discussed at this conference. And so Feynman was also there. And here's, of course, Feynman's inimitable answer to the question that Goltz asked, simply yes. And we are very lucky that there's a full transcript of the conference. Cecile DeWitt helped to put that together, and in collaboration with the Max Planck Institute for the History of Sciences, you can actually download the whole transcript of this conference for free on the internet. I suggest you to do that. It is highly entertaining. And even more so that if you look at the current literature, there's a lot of literature over the last almost 10 years now on that topic. And I claim that 95% of things that are being discussed right now in the literature are exactly the same things that have been discussed, just with a different set of people, but very similar answers. So this was Feynman's point. So Feynman said, yes, of course, we can have phenomena that cannot be explained by just using quantum theory and GR. And here's an example. He said, let's just design an experiment that uses a gravitational link and has some sort of quantum interference with it. And the Gedanken experiment that he gave was, how about we have some object, a massive object like a mass, with an internal degree of freedom, spin 1/2, for example, and you send it through a Stern-Gerlach type device. This is what is depicted here. What happens is the center of mass degree of freedom will, in the Stern-Gerlach device, result in a superposition. So basically, you generate now your massive object through the Stern-Gerlach device in a superposition of macroscopically distinct states of the center of mass degree of freedom. It's just a Stern-Gerlach, but now just with a single silver atom, you take a huge object that has a single silver atom inside with the spin. You just need a little bit larger field gradients. So you create now here a superposition of this mass here being down or up, okay, and up. And then you have a second mass that just couples gravitationally with our first mass. If the first mass is in a superposition, then obviously what happens is you have your two branches like in our neutron experiment, but in that case now, this thing here is the source of gravity and not the Earth. So what happens is you have in this branch, you interact with the test particle, and that branch you interact with the test particle. You get two different gravitational accelerations now in a superposition of the two branches, which means that after some time, the one branch here will be less accelerated than the other one. And so you end up after some time in an entangled state between the two masses. Because now you have correlated position and momenta between the two masses in a superposition, aka quantum entanglement. Yeah? Very simple. Now, so you could say, so what? That is obvious. Okay, so everyone who did a quantum mechanics 101 course would say, of course, this is what you would expect. But here's the problem. Okay, so from a quantum perspective, super easy. From the gravity perspective, here's an issue. Okay? Because our current theory of gravity is a classical field theory. So that means any mass configuration, any source mass configuration, no matter what, you have a source mass configuration, no matter how much you do in the lab, you put a black box around it, and your classical field theory will tell you that the space-time you create with this mass configuration is a fixed space-time. It's a classical metric within which any test particle will follow a geodesic. That is the dynamics. So whenever I start out in such a situation where my test particle couples to any metric whatsoever, it will follow a geodesic and will never ever evolve into some sort of superposition in two different branches. So according to classical field theory, you will never ever see entanglement. So seeing entanglement is one example of a phenomena that we could not any longer explain by assuming the joint validity of quantum theory and a classical field theory of gravity. Okay, now there was another, so I think it was like 20 physicists at the Chapel Hill conference. Another one was Louis Witten. He was also there, the father of Ed Witten. And he asked the next relevant question. He asked, what prevents this from becoming a practical experiment? And this is going to be the rest of my presentation. Okay? This is the question we want to ask now. Or in other words, how crazy is it to think about this becoming a practical experiment? So again, I think the foundations were laid with Feynman's Gedankenexperiment. And then over the last couple of years, several implementations, possible implementations of such a Gedankenexperiment have been discussed in the literature. And there are essentially two possibilities how you can generate entanglement. The one is you have your two masses. Okay, so both of them are actually large enough to create a sufficient gravitational interaction. And you just have your two masses as two quantum harmonic oscillators. Okay, assume you have two quantum harmonic oscillators that are just coupled via gravity, then they will become entangled. So from the quantum information perspective, the 1/r potential, if you Taylor expand it, the first non-trivial interaction part is an XX coupling. It generates a two-mode squeeze state. So this is all in the realm of quantum optics. So we are almost back to our Einstein example. But the point is, if you have two quantum harmonic oscillators and you couple them with a 1/r interaction, with a gravitational interaction, they become entangled. Okay? So this would be one possibility. And you can ask, what is the, okay, let's first say, what's the other possibility? The other possibility is, start with what Feynman said, let's create a superposition. Really a superposition of macroscopically distinct center of mass states. Right? So basically have a particle in a superposition of being here and there. And then your second particle, the test mass, is also in a superposition. Now what happens? What happens is our cow experiment. Remember, the neutron when propagated through the gravitational field of Earth and picked up a dynamical phase. That's exactly what's happening here now. So this particle here sees the gravitational potential of that one, so it will pick up a dynamical phase. And since this is in a superposition, it will pick up a relative dynamical phase. And what you have now here is what in quantum information we call a conditional phase gate. So basically, you have now two qubits that you initialize, and you have a conditional phase that is evolving. And once the phase value, the conditional phase hits -1, the thing is entangled again. So this is basically another way to generate entanglement between those two systems. Fun thing, even though it sounds like these are two extremely different ways of generating entanglement, if you ask what is the rate at which this interaction occurs and at which you entangle, the rate is the same for both cases. The rate at which those two cases entangle is, first of all, obviously those two constants have to enter. So there's Newton's constant and Planck's constant. It scales with the square of the mass, well, because they couple gravitationally. It scales with the delocalization of the wave packet, which is in this case of the oscillators, just the Gaussian delocalization of the wave packet of each oscillator, and which is in our superposition, just the distance of the center of mass states in a superposition. In both cases, it's well defined. It essentially means in classical analog, the more drive you give, the larger drive amplitude in the action, the larger will the interaction rate be. And it goes with 1 over the distance of the two center of mass systems to the cubed. Because this is the, remember, if you Taylor expand the 1 over r, then the first non-trivial part will be, which is actually the gradient of the field will be the 1 over d cubed. Yeah, so this is the scaling. Now, the question you should ask, because now we want to talk about real experiments. Yeah? So what does it take? There are so many beautiful atom experiments out there. Why not just take two atoms sitting in an optical lattice and letting them interact? Yeah, let them interact for seconds, for hours. Yeah, this is the beauty of atomic physics experiments. Okay, let's ask how long does it take to generate entanglement if I have two atoms which are separated by a micron? Okay, well, the answer is simple. It says here 10 to the 24 seconds. That's too long. Lifetime of the universe is what, 10 to the 18 or so? So we'd say it's only 6 orders of magnitude. Yeah, but it's only 6 orders of magnitude compared to the lifetime of the universe. So the alternative is, let's take two lead spheres. Let's take a lead sphere of like 50 micron size. That's not so bad. It's large, but it's not totally crazy large. And separate them by 100 micrometer. And then you ask, how long does it now take to generate entanglement? And the answer is, see, 10 milliseconds. That's not so bad. So whenever, as an experimental physicist, you bump into a time scale that is below 100 milliseconds, you sort of are happy, because that's, at least as a quantum physicist. No, this is so suddenly things become not totally crazy. So now the question is more, how crazy is the 50 microns? Yeah, which is going to be the rest of the talk. Okay, so everything boils down. Let's rewrite this now, okay? So obviously, this entanglement rate needs to be larger than all possible decoherence rates in the system, which means you need to maintain quantum coherence over a certain amount of time. So you have a coherence time in your experiments, and if you just rewrite that expression, we now have the following condition. For any experiment that wants to demonstrate entanglement through gravitational interaction, in an attempt to demonstrate a phenomenon that cannot be explained by using quantum theory and Einstein's general theory of relativity, this is the boundary condition that you have. The product of these 4 parameters, the mass square, delocalization square, coherence time, and 1 over d cubed, the distance, center of mass distance, needs to be larger than h bar over g. So whenever you want to try something, first you need to check whether this is fulfilled. Okay? The beauty of that expression, and I like it so much, is that you can separate now. Yeah, you can separate quantum experiments where you can simply try now in the lab to maximize that number. Perform quantum experiments. You can even do that on single systems. You do not even need to couple. Just take a single quantum system and just try to maximize the mass, maximize the delocalization of the center of mass degree of freedom, and maximize the coherence time. Just see how large you can make this thing here. Yeah? And independent of that, in your other lab next door, you build an experiment where you try to minimize the distance between two masses for which you can still isolate gravity as a coupling force. Okay? Because all of that, of course, all of these interactions are gravitational. And obviously, if you make this d arbitrarily small, your interaction blows up arbitrarily, but obviously there are other forces than gravity in play. So experimentally, you need to know very well when other and how other coupling forces start to take over. And you can imagine electromagnetic interaction between two particles that come close will start to dominate at some point. So the question is, if you do gravity experiments, how close can you actually bring two masses and still demonstrate that they gravitation interact and make sure that gravity dominates in those interactions? Okay, that is the challenge. Okay, so I summarize. This is more or less, I could have started the talk like that, okay? But I just wanted to give you some motivation, why this is an interesting question. So the question that we're asking is, can we have quantum systems as sources of gravity? And in order to address that question, we need to answer a question, we need to address two other questions, namely, how small can we make a source mass in gravity experiments and how close can we bring them together? And how massive can we make a quantum system? Okay, so now I will tell you where we stand. And then you can judge for yourself whether the question is a meaningful one or not, okay? So, reality check. Here's a plot. Look, here's coherence time for experiments where existing quantum experiments where the center of mass degree of freedom is delocalized. This is mass, the mass of the objects in those experiments. And we have a quantum realm and a gravity realm. The gravity realm obviously does not have yet any entries on the y-axis, but that's the goal. So when we started looking into that, let's focus first on gravity. So how small can we make a mass in gravity experiments? When we started to look into that, so the smallest source mass that people had been using in experiments on Earth was on the order of a gram. So let's very briefly look at the history of gravity experiments. Here's one very famous one that predates the Cavendish experiment, the Maskelyne expedition to a mountain in Scotland, Mount Schiehallion, where they actually demonstrated the gravitational attraction between a pendulum and the mountain. And actually the idea was to measure the density of the Earth in those early experiments to test the conjecture by Newton. And they basically measured the displacement of the pendulum with respect to the fixed star horizon. It was a beautiful experiment, however, with a large error bar because they did not have a good finite element model of the density distribution of the mountain. And this was the big advantage of Cavendish's then tabletop experiment, who had a much better control on those parameters. And if you read the original Cavendish paper, he actually references Maskelyne's work and actually shows where his experiment is actually better. And I always have to laugh because I'm from Bavaria, and the fact that they call that a mountain is very funny. So anyway, now if you fast forward again time, if you look into the 2000s, so 200 years later, and we now have these absolutely fantastic tabletop precision experiments of gravity. Here the Earthwash group of Eric Edelberger at the University of Washington has really been leading over decades. And you see here typical source masses of some kilograms in those precision measurements of gravity. So when we looked into that, we asked, well, can we make things a little bit smaller? What about we take a small gold sphere, so, you know, a second one, you shake it. If you shake it, you know, you have an acceleration modulation, the position of the second one. Yeah, and then with modern optics methods and so on, maybe you can even just do an optomechanics experiment where here's the source mass that you shake, and here you just have an oscillator that you can read out optically, and then you should be very sensitive. So we started looking into that, and eventually the first experiment that we did was really a simple gold sphere of 90 milligram that we were, you see, oscillating like that. There was a Faraday shield shielding electromagnetic interactions, and eventually we had a torsional pendulum with a simple optical lever readout to monitor the displacement of this gold mass on the torsional pendulum. The mass, again, was just 90 milligram. The acceleration modulation due to displacing the mass by a few millimeters was on the order of, we have it here, 10 to the minus 10 meters per second squared. This translates into a displacement modulation of a few nanometers, which you can, of course, easily measure here on the torsional pendulum. The more interesting part is the fact, of course, now that you have to hang this pendulum in your lab, and you have to hang it such that you can still resolve nanometer displacements in your lab environment. So here's the pendulum, and here's a time trace. You see during the day it's a little bit rough. The variance is quite large. Then during the night, variance becomes smaller. So here you can really measure. Okay, and then you see a bump. You see that bump? That's a night bus. Okay? Another bump. Here a bump. That's a late night bus. So the Austrian press was joking that this was the most expensive traffic monitoring system that Vienna has come up with so far. But the point was, this already showed us, well, I mean, this is just one example of many, okay? The Vienna City Marathon was like 1.5 miles away from our lab. The winner entry, that was amazing. All the pendulum went just haywire. So it's, nevertheless, we obviously then took Christmas, because during the Christmas time, there was not so much traffic going on. And you see, just focus here on the red and the yellow. The red is the actual force response of our pendulum. The yellow are the force residuals. So you basically subtract the expected gravitational signal from it. And you beautifully see that they go essentially down to nothing at the location of the modulation. And you even see a higher order response because what we modulate is a 1/r potential. So basically, it's a nonlinear potential, a gravitational potential, 1/r, that the pendulum reacts to. So you get first order, second order, and third order is just buried in noise. At the end of the day, where we could resolve easily this acceleration modulation with a precision of 1%. So the precision of our experiment was really on the order of 10 to the minus 13 G, small g being the Earth's gravitational acceleration. And the systematics was also good. So we basically had we had a 9% 9% deviation of Newton's constant and the coupling, but this was all covered in our known systematics in the experiment. So that's an example where we were now for more than 90% sure that let's say that more than 90% of the interaction is gravitation in that case. So that's dominating gravitational interaction on the level of a millimeter scale object at a surface distance of down to 400 micrometers. Okay, so that's that was the result of that. The next step is, of course, now we need to go smaller. Millimeter is still like way too large. It's like 10 to the 22 atoms or so. So the next step is this here. So basically using this one now as the source mass, which would be let's say 50 micrometer gold sphere, which corresponds to on the order of 10 to the 18 atoms. So this is on the order of the Planck mass. Yeah? But there's no way that we can do that in our lab in Vienna. Again, the night buses were just one example. So what we do now is we have moved our experiment underground. So we are now here located in this tunnel. Here this is Hans setting up the experiment. You see Hans is wearing a cap. And the reason is that this tunnel here has an exceptional temperature stability. So the temperature is stable down to a few millikelvin, but around 7 degrees Celsius. So it's really cold, and in particular, if you go there in the summer, you tend to forget your jacket, which is a very bad idea. But the lab is extremely stable. The first data looks very promising. So we have now masses that look like that. So they're micro fabricated. These are now the source mass and the order of the Planck mass. We have them on a disk, you see, and we rotate that disk now in the presence of the pendulum. And now this is an experiment that is more or less almost running, and we hope to have the next. This time we don't need Christmas, but maybe by Christmas we have some results where we see gravitational coupling from Planck mass objects. Okay, so this is the summary of our gravity attempts. You see, this was gravity when we started. We now are somewhere here with our source masses, and then we go to the Planck mass, which brings us somewhere here on the mass. So this is the level of source masses for which we think we will know that we can isolate gravity as a coupling force. Yeah? The next thing that we are going to do is we're going to focus now on the distance. So we are now trying to do experiments where we minimize the distance between two masses and still maintain gravitational coupling. So for people doing, this is just a comment for the experts, there are people doing so-called inverse square law tests of Newton's law. This would correspond to a test on the 10 micron scale for alpha equals 1. So we really want to do experiments where gravity dominates. This is the whole point of our attempts here. We want to understand what it takes experimentally to isolate gravity as a coupling force for small masses such that we can make them quantum, and small distances such that we can ramp up the interaction. Okay, so let's finish now the talk by briefly looking into the quantum regime. We know what's required. Okay, so now let's look where we are. Here are two of my very favorite examples when it comes to quantum experiments with delocalized center of mass degrees of freedom. The example of Markus Aspelmeyer's beautiful macromolecules I already showed you. So you see, this is like a macromolecule with 2,000 atoms. Superposition very large, so our delocalization is 500 nanometers. Okay, and the mass is small. Well, that's life. So we could go to solid state mechanical oscillators. So we have ways either via optical or electromechanical interactions. We can actually control the states, quantum states of motion of solid state oscillators. And here's one beautiful example is by Andrew Cleland back in 2010, where they looked at thickness oscillations of an aluminum nitride slab. It was a freestanding slab, a little cantilever, that was coupled capacitively to a superconducting qubit. And what they could do now with a resonant coupling, they could actually, through basically driving Rabi oscillations in the system, they could actually create energy eigenstates of the system and even create superposition states of different energy eigenstates of the acoustic modes of the system in this experiment. So in that case, you see the mass is much larger. They have 10 to the 13 atoms. So that's a jump of 10 orders of magnitudes in mass. The collective center of mass, 10 orders of magnitude. Okay? The problem is the delocalization. In that case, the effective delocalization was on the order of sub-femtometer. That's small. They could still, I mean, if you look at the paper, they see beautiful Ramsey interference oscillations. So they could show that they do have quantum interference. They could show that they had a superposition. However, the displacement is very small. So if you put the numbers now, if we compare our numbers. So if you now plot, or if you compute m delta x squared times the coherence time, remember this is our relevant numbers, and we compute that in units of h bar over g. Okay, and we assume that this is some virtual device that we could use for gravity experiments with a separation of 10 microns. Okay, this is just arbitrary, but just stay with me. And so then this value should be on the order of 1. You see, way to go. Okay, that's 18 orders of magnitude. What about Cleland? Cleland, well, 10 to the minus 24 orders of magnitude. There has been a recent advance in Yiwen Chu's lab at ETH. They ramped up the mass, and they are also now on the level of 10 to the minus 17. Okay, so we are basically now on par, matter wave and these things. So it's just 17 orders of magnitude. Yeah? So how do we proceed now? Now I give you the fast forward, because on Friday we're gonna have a more detailed technical seminar. So I just give you the gist of it now. What the things that we want to consider now for the future is we obviously, because we need mass. There's no way we can go around mass, so we need to focus on a system, and the system of choice is really solid state system. So we really want now to look at the center of mass degree of freedom of a solid state object, because there we can pack a lot of mass into a small volume, meaning we have high densities, which means we can lower the distance, which ramps up everything. So everything is, this is the way to go. Large densities, solid state densities, and such center of mass degrees of freedom. Now, Jack has already mentioned it. There has been quite some efforts over the last, what now, 15 years maybe, in controlling mechanical motion using the toolbox of quantum optics. And I don't go into the details here, just let it be said. The whole idea is that in most cases, you take a mechanical oscillator, you couple it to a optical or some other, let's say, microwave cavity, such that the mechanical motion changes the properties of this resonator. Okay? And once you have that, you see you can now, the mechanical motion changes the radiation states of the resonator. So you can actually use the mechanical motion, you can manipulate the mechanics in order to generate quantum states of light. But vice versa, you can also use quantum states of light, coupling through this interaction to our mechanical oscillator to generate quantum states of mechanical motion. So if you want to hear details, Friday is the time. And let it just be said that at the moment, through I would say 15 years of collective hard work all around the world, the situation that we have now is an absolute fascinating one. So when when Jack and I started in this business back then, 2006 also, this was a dream, but now it's really, we have mechanical systems in the quantum regime all over the world in many different facets. Ground state is like nothing these days. We have squeeze states, non-Gaussian states, entangled states. So you just name it, okay? This has really been a great success. Now, the question is, does any of that help us with our actual goal? Large delocalization, large mass and gravitational interaction? And the answer is probably not. Because most of these systems that you see here are harmonically confined oscillators. And if you try to really generate large delocalization of a system that basically has a spring constant with it that wants to go back, it's a hard task to do. I mean, you could do it with some means, projective measurements and so on, but the time scales that you have are slow, So you need to come up with something better. And this is what we actually came up with. Well, we didn't come up with it, but we followed this idea was, why don't we combine the beauty of what people have in matter wave interferometry and atoms, namely the fact that atoms are just live freely, happily ever after in vacuum. They don't couple strongly to the environment, so you can reach long coherence times with solid state systems. Yeah? And by getting rid of this harmonic confinement and just levitate solids, yeah? Instead of having solids that are clamped. So that was the idea. There's a lot of benefits, as you will see in a second. So how do we do that? Well, typically you just use a dielectric particle and you focus a laser beam very strongly with a microscope objective. Why does that help? Well, because if it's a dielectric object, you have an induced dipole. Okay, so the potential landscape that the particle actually sees is the dipole moment times the electric field, where the dipole moment is induced because it's a dielectric object. So you have an electric field, the laser beam that comes induces a dipole moment. which is the polarizability times the electric field, and that leaves you now with a potential landscape that is proportional to the intensity of the laser beam that the particle sees. So if I have a Gauss beam as an intensity, the potential that the landscape that the particle sees is an inverted Gauss, which for small displacement is just an harmonic potential. So if I now take a focused laser beam, then I have in all 3 dimensions, I actually have a confinement that for small displacements is harmonic. And so a focused laser beam gives you 3D confinement. And I have now a 3D harmonic oscillator that I basically can interact with now. Okay. So let's do that. We put that whole thing in vacuum. We use the light that we trap the particle with. We use it to pick up actually the signals that also tells us about the motion of the particle. And in a feedback loop, we can use that to stabilize the position and just pump down the whole thing and have then a particle kept in ultra high vacuum. Okay. The next thing you do is you ask the question, how well can I measure the position of the particle? And if you're clever, you see that the light that is back reflected from the particle carries all the information, almost all information of the position along the axial direction. Okay, so what you do now is you build an intelligent confocal backplane imaging system, essentially a microscope technique that was developed in neuroscience, more or less. And that allows you, if you align your system right, to now monitor the displacement of the particle with a precision that is close to the Heisenberg limit. So which means that the product of back action and imprecision of the particle measurement is only a factor of 2 away from the Heisenberg limit, which means you can now monitor the motion of the particle at room temperature in ultra high vacuum with a precision given by the quantum ground state size of the particle. So you can actually monitor now in real time the quantum trajectory of the particle at room temperature. This is now a particle with 10 to the 9 atoms, and you follow now the quantum dynamics of the thing. You can be a little bit more advanced. Actually, you can do a state reconstruction for the phase space by using a so-called Kalman filter. And if you have that, you can, of course, also not just follow the trajectory, you can stabilize the trajectory in phase space. And if you stabilize that, then what you do is you basically put some electrodes here on your microscope objective and the collimation lens. You can do electrostatic feedback. You stabilize the position in phase space with a precision given by the ground state size, which means you stabilize the particle in its ground state. That's called ground state cooling. So we have just prepared now a room temperature particle with 10 to the 9 atoms in its quantum ground state of motion. Okay, so that's it here. That's an image of a room temperature silica, so a glass particle with 10 to the 9 atoms cooled into its quantum ground state of motion. And so this solves the big mystery. Okay? Do you remember the Einstein, the Event Horizon Telescope images of the black hole? Yeah. So quantum, gravity. So here the difference is gravity is orange, quantum is green. This solves all the mysteries. Yeah? I wish we would have published those pictures at the same time. Seriously. We were a little bit too late for that, unfortunately. Okay, so I will finish now. Okay, there are many other ways of cooling, which I will talk about on Friday a little bit more. But of course, the question is now we need to delocalize. Okay, that's the big promise. How can we delocalize this thing? Well, and one of the possible things to do is now, of course, and that's the beauty of the trap. Right? Just switch off the trap, switch off the potential. The thing just free falls. The wave packet will just disperse. And already after some milliseconds, you will have a wave packet of the size of the particle itself. You start off, typically in our case, with like 3 picometer ground state extension, a pure state wave packet. Now just let it expand for some tens of milliseconds, and suddenly you already have a wave packet as large as the particle. And you could even be more clever. This is proposals by Oriol Romero-Isard from Innsbruck. You could, instead of having an harmonic trap or switching it off, you could actually invert the potential. You can have the thing ride on an inverted potential, and then you get exponential increase in time of the size of the wave packet. These are possibilities that you can explore. How would you explore that? Well, by using what I just told you. Now, we know now that the intensity profile that the particle sees is nothing else than the potential landscape. So if you want an harmonic potential, use a Gaussian beam. Okay. If you want a quartic potential, use a flat top beam. If you want to have a double well or an inverted potential, even here an inverted potential, use a TM01 mode, like a Gauss mode. Okay. So now just start using other intensity profiles and you can start manipulating the potential landscape that the particle sees. And these are now the things that we actually need to do, and these are the things we are working on. So this is right now the big outstanding questions. We already started discussions today in Michel's lab. I really hope that we can sort of gain some inspiration from the absolutely amazing experiments that you have been doing and still are doing, and give some insights how we can now go from our pure state wave packet to some actually macroscopic superpositions. Okay, so the only thing that's left is how do we get from 10 to the minus 17 to 1? Okay, I give you a quick glimpse and the rest on Friday. Here's the possibility. Okay, so why not using superconductors for levitation? You have high densities, you can make them large. So here's an example of a 100 micron thin lead sphere that is levitated at 20 millikelvin. You can couple the motion to superconducting devices, superconducting circuits. Okay, you can in principle do similar things. And in principle, if you have the right protocol, oops, I don't have it here. If you have the right protocol, then you can go close to 1 if your delocalization is large enough. So basically, here's the example. You see, for a Planck mass lead sphere, if you would have a delocalization of 12 nanometers of the center of mass, okay, then moderate temperatures of environment and the particle would be sufficient. So the challenge for you now is, can I give you a Planck sphere, Planck mass sphere? So let's say a 10, 20, 30 micron lead sphere, and you give me a delocalization of 10 nanometers. You can do that. I happily invite you to come to Vienna. And we're in business. Okay, very good. So let me stop here. I have my FAQ slide because I learned some of the questions should be addressed immediately. Here's what we do not learn from observing entanglement generated by gravity. Okay, so this is basically just my repetition slide. So generation of entanglement through gravity, okay, is number one, inconsistent with assuming gravity is described by classical field theory. And this is my main statement. Okay, this is the most important message. If you manage to do such an experiment, you show that a classical field theory of gravity is not, this an experiment is not being described by a classical field theory of gravity. This does not tell us anything whatsoever about the quantization of gravity. Okay, I just want to make that very crystal clear. This is like, you know, if you, it's hard to actually, how to say, if you don't measure photons, you can still have a superposition of electromagnetic fields, but you still cannot conclude on the existence of photons. Okay, this is similar here. It definitely might very well be that the generative entanglement is consistent with a quantum field theory of gravity. Okay, I mean, we know how to write that down. There exists, we do have working quantum field theories of gravity, and highly likely, if one sees entanglement, they will be described by such theories, which doesn't prove the correctness of them, it just proves the consistency with them. Yeah, just okay. It also, and that's my last slide, it excludes by principle all gravitational collapse models if you see entanglement, which is another motivation maybe to do that. Okay, I don't comment on the last part, but just finish now. So here's my summary. We are basically now exploring in our lab in Vienna these two regimes. We're exploring levitated systems, quantum systems pushing to larger masses, larger delocalizations. We are pushing gravity experiments to smaller scales and smaller distances with the hope that at some point we can explore the interface of those. My biggest thanks, of course, goes to my group. This was a visit to Einstein's house at Kaput, close to Berlin. This was a gift to Einstein, this house. And with that, I thank you very much for your patience.
Okay, well, time for some questions. Rodrigo?
So my question is about your main statement that I understand it better. So if I assume a classical interaction between two quantum particles, I just have a negative proposition on one, and that will create entanglement. So from the quantum perspective, everything works. I think that's what you mean. But then you said that there are general relativity arguments of the metric and these propositions.
Yes. Yes. Oh, you just said it. So, but coming. So, okay. I guess the point is, this goes back to your first question, okay? Because basically, I guess in your back of the mind you have, well, but you know, we have Newton, okay? If I take Newton, there's nothing. Yeah? There's actually also nothing from a gravity point of view, and this is correct. If Newton's theory of gravity would be the correct theory of gravity, then we wouldn't even discuss here, because Newton's theory of gravity is instantaneous, it is action at a distance. Right, and of course, any action at a distance can entangle arbitrarily. So this is there's no magic behind that. Okay, but the problem with a field theory is that the field configuration is a solution of the field theory. Okay, and if you start off with Einstein's field theory, or with any field theory, in order to explain those experiments, so you linearize the field theory, you end up in some sort of Poisson equation that actually describes to you how the source, so the meta distribution, generates the field. Okay, so a Poisson equation with the density of matter and the field. Now I give you a superposition of center of mass degrees of freedom. What do you put in the Poisson equation as the density of your mass? You cannot put a superposition; it doesn't exist. Yeah, you can actually, because you cannot put the energy momentum, the stress energy tensor there, because it's an operator, right? And you just cannot handle it.
What you're saying is that it's not linear enough to admit that the proposition of solution to be a solution.
No. That's not what I'm saying. No. I'm saying, as a classical theory, it cannot handle by principle operators. So what you need is so basically, if you have a superposition of two center of mass states, the way a classical theory handles it, it says, oh, I have half of the mass density left, I have half of the mass density right, and this is now the source of my gravitational field, okay? Which now gives you a gravitational field sourced by half my mass here, half my mass there, which is not equivalent to a field generated by a superposition of the two masses.
So can we compare the proposal to the situation that exists when you consider the van der Waals force between, let's say, two arguments?
Yes.
So the interpretation of this van der Waals force is the fluctuating electrostatic dipole of the shadow.
Mm-hmm.
So we still have to, we have a sort of classical interaction between the two electrons, but we have to take into account the fact that they are in superpositions of position state. Wouldn't that be a fair comparison to test the equivalent of the van der Waals interaction, which is essentially can only be explained by quantum equations?
No, I think I agree. Yes. And this is, I think, on the level of electromagnetic interactions, arguably, I would even claim that if you look at certain trapped ion experiments also, that some of the gates explore exactly also that coupling mechanism. Yes. No, I agree. This is there definitely are electromagnetic analogs of that. Yes.
So in that kind of explanation, I think it's one of your lines at the end. So you do not test directly the field compensation.
Yes.
That's the fact that it's not just two distributions interacting.
Exactly, yes. You show that you require at least the assumption of the superposition principle to be valid. Well, it's delocalization in the most general ways. Thank you, yes.
Okay, maybe time for one last question, given the hour. Vitek? Yes, lots of pressure.
So it seems that the principle behind the experiment has nothing to do with gravity. It's testing interaction between two superpositions. Is it possible at all to have an interaction that remains classical, and then without you concluding that quantum mechanics fail? Is it possible to imagine such an interaction that would remain classical by your definition, concluding that quantum mechanics is just...
Yes. Well, to answer first your question and then comment on the first part, I think that this is exactly what people like Roger Penrose would assume. So there's a firm belief of some people in the gravity community that gravity will remain by principle classical. And the only way that if you now want to do an experiment like that, this can happen is that quantum mechanics fails. So actually in my discussions with those people, Roger expects this experiment to fail. Because any attempt to, in this view, any attempt to generate a superposition with a sufficiently large center of mass delocalization will result in some new physics that decoheres the state. He calls that the gravitization of quantum physics instead of the quantization of gravity physics. Yeah. But I would briefly say with your first part of your statement, what I showed, of course, requires gravitational interaction. So and in that case, it tests gravity in a situation where the source of gravity is delocalized in a quantum manner. So that's, I think. Okay, good.
Okay. So just keeping an eye on the time, let me just remind all of those who still have questions or would like to discuss further, Markus will be here all week. Please feel free to reach out to him by email. And then let's just thank him one more time.
Thank you.